Okay, so welcome back. This is our sixth video about Markov networks, and we're going to discuss now the condition random fields, or CRFs. So let's introduce the idea of condition random fields using one application. And let's suppose that we are interested in recognizing handwritten words. So we're going to have as input something like this. It's going to be a word as a sequence of images, and we have one image for each letter. So something that we can do is to use machine learning classifiers and train those classifiers over the images in order to recognize the letters. So in this case, we're going to take one single image and we're going to give it to the classifier, and the classifier will output to us something that approximates this probability here. Is the probability of the label that's going to be one of the letters given the image. And we can use that classifier to label the remaining letters, right? So that's going to be independent runs. So we're going to use, if you have any letters in the word, we're going to run the classifier any times, and each time it will come out with one output like this. This output does not need to be a probability. Many classifiers, they just output a sort of a score, but this score is proportional to the confidence that the classifier has in each label. So one limitation of this approach is the fact that we do not take into account how likely are a sequence of letters. So if you look at this example here, the classifier may be a little bit unsure about the second letter here, the X2. It might be an U or a V, but if we look at the different words that we have in the English language, you're going to see that the sequence QU is a lot more common than the sequence QV. And we can use that information in order to improve the accuracy of this classifier that's going to recognize different words. So what we are interested is actually in a system that can provide us the probability of y given x. And this y here is the sequence of labels that we have in the word, one label for each letter. So we are interested in this joint probability here for all the labels given all the input images that we have. And that is exactly what the conditional random fields, or the CRFs, are going to give us. They are a discriminative model that approximates this conditional probability here of the probability of y given x being y, the all labels that we have in the sequence. So discriminative models are slightly different from the generative models, and so far in this course we have studied the generative models. So the generative models, and we're gonna come back to this topic again in this video later on, but the generative models, they try to model the joint probability distribution for all variables that we have in the problem. And differently, the discriminative models, they try to model only the probability of y given x, being y one particular variable that we are interested in. In this case, it's going to be the class variable. And if we use independent classifiers in order to compute this probability here, that's going to be the probability for all the labels together given one input image x, that's going to be the sequence of letters. What we can do is simply to assume that the output of the classifier is going to be independent. So we're going to multiply all the probabilities given by the classifier. So we're going to take the probability of y1, that is the first label, so it's going to be the probability of y1, that's the first label, given x1, that is the first letter, times the probability of y2, that is the second label, given x2, that is the image of the second letter, and we're going to keep in doing that and multiplying until we have the last letter. In this case here, we have 5 letters, so it's going to be until the probability of y5 given x5. And when we provide one image to a classifier C, what we're going to get as output is a sort of a table where we have all the possible class labels. In this case, it's going to be all possible letters, and we have 26 letters here. And for each letter, we're going to have associated one number. And this number is the probability of that letter given the input image that we have. So we can see this table here is a sort of a factor, right? So we have a factor that I'm calling this factor the phi1 of y1 and x1. And the idea of this factor is to assign higher values to the labels that are constant with the input image. So in this case here, we can see that the classifier is pretty confident that the input image is for a letter Q. And we're going to do the same thing for all the letters that we have. So we input this image of a U to the classifier, and we get another table that we can see as another factor. In this case, I'm calling that phi2 of y2 x2, and it's going to be the probabilities for the second label. And in this case here, we can see that the classifier is not so sure. So it is associating similar values to the letter U and the letter V, and it means that the classifier is not so confident. And this is a situation that we can help the classifier by inputting the information about how likely it is to see the letter Q with the letter U and the letter Q with the letter V. And that's going to be done by introducing a new factor. So we can introduce a new factor that I'm calling here the phi y1, y2, because we are looking at the first 2 letters. And that factor will measure the affinity between 2 letters that are appearing in a sequence. So what we can do, we can take a dictionary of words in a certain language like English, and we can look at pair of consecutive words in the dictionary, and we can count how many of those pairs we can find. And at the end, we normalize that, and we can use that as information for this factor. So in general, we're going to have a factor in this form here. It's going to be a factor phi of yi and yi plus 1. And I'm assuming here that if you look here, I'm not putting the index I here because I'm assuming that this factor is going to be constant. So we're going to use those parameters for the entire model. And that is an assumption. So I'm assuming that the sequence of the letters will not depend, so the probability of the sequence of the letters will not depend on the position of the letters in the word. That might be true or not. I'm not sure about this, but it seems to be a reasonable assumption that's going to simplify and reduce the number of parameters here. But to be completely clear about that is just an assumption that I'm making for this example. This is not one assumption of the model. So what we got at the end is an indirect graph like this one, right? And we call this the linear chain CRF. And we're going to recognize this, and it is very similar to the hidden Markov model, but in this case we have an undirected graph. And if we want to compute the probabilities, what we do is to compute the probability of y given x. Take a look at I'm not computing the probability of y and x or the probability of x. I'm computing the probability of y given x. So I'm not interested in having a generative model that can model the dependencies and independencies of all variables that we have. I'm just interested in modeling this conditional probability because I want to use that model in a classification task. So in this case, what we have is 1 over the partition function, and that's interesting here that we are writing z of x and not just z. And that is because this partition function here will depend on the input that we give. It's very simple, so we can just clarify this. If we look at these factors here, the phi I, they will depend on the input x. For different inputs, they're going to be different. Remember that those factors, they have the probabilities that we have for the different classes for a given image. So if we input a word like this quest, so the factors will be different than if we input any other word in this model. So the partition function that's going to be the sum of all the probabilities for all the possible assignments that we have will depend on the input x, and so that's why we make this clarification here by writing z of x and not just z. So this is one explanation for why we call z the partition function and not the partition constant, is because for some applications this partition function depends on something. In this case here, for the condition random fields, it will depend on the input x, and the probability will be the Gibbs distribution. So we're going to factorize the joint probability given the Gibbs distribution, and basically what we have is a pairwise Markov network. So we have this, these factors here that we call the phi y. So going to be phi y, and we have those factors here that we are just calling the phi. Right? And this here will depend on consecutive labels yi and yi plus 1, and this one here will only depend on the input x and the variable y. So it's going to be phi I of the yi and xi. So we multiply this all together. We're going to have in the first iteration, we're going to have just this information here, and the second one we take in account this guy and also the connection between the consecutive words. In the next one, we're going to take this guy here and the connection between consecutive words, and we keep doing that until we get to the end of the sequence. So what kind of answer we want from this model? And it's very clear that we are interested in the most probable instantiation, so what we call the map or MPE query. So at the end, what we are really interested is not in the probability, but what is the sequence of letters that is the most probable one given the input word. So in order to compute that efficiently, we need an algorithm that we haven't seen before, that is the Viterbi algorithm. And we have already discussed the Viterbi algorithm when we saw the hidden Markov models. So basically it's the same algorithm. So we can see that the linear chain CRFs are underwrite versions of the Markov hidden models, so we can use the same algorithm that we haven't seen before in this case here, just adapting the idea of transition in time, that now we have a similarity between consecutive words, and adapting the idea of observing an emission that in this case here will be an output provided by a classifier. And we can extrapolate this idea of the condition random fields that we just saw for the linear chain to more complex graphs. So there is one area of research that we call the structure output learning or structure output prediction, that we are interested in predicting and classifying structured objects that are not just discrete values or real values that we have in classification or regression. So that's going to be applicable to chains and sequence, as we saw, but also to more complex structures. So in the case of an image, I might be interested in labeling the image according to the objects that I can find in the image. So for instance, you could say that given this image here, I'm interested in saying that we have the grass here, and also in all this area here, and we have a call here in the middle. So we can use condition random fields for this task, and usually it's done in the following way. So the first task is to segment the image. So I'm going to divide the image according to the color of the pixels or other characteristics. After I have segmented the image, I'm going to use a classifier to classify each segment. So we see here what is the output of independent classifiers. And we can see that the quality is not very good. So we can improve the quality by using a conditional random field. So the idea is the same that we developed for the linear chain. We're going to connect areas that are neighboring areas in the graph, and they're going to run a map or MPE query in order to see what is the assignment with the highest probability. And here we can see the quality of the results. So it's much better than before when they had the independent classifiers. We can see that we could identify the road, the car, and the building. So originally we have these areas all shattered in small pieces. But what we can do is that all the areas that have the same labels, we join these areas together. So at the end we have just these three areas here, one for the road, one for the car, and the other one for the building. And in this image here on the bottom, we have just the grass and the call. So condition random fields are discriminative models, but in this course we have focused much more on generative models. So we have seen, for instance, Markov chains, hidden Markov models, Bayesian networks, Markov networks in this lecture, and these all are all examples of generative models. The difference here is that the generative models, they model the P of X, being X the set of variables that we have in the graph. And a good thing about the generative models is that those models are not fixed to a single task. So as we estimate the probability of all the variables together in the domain, we are free to ask different probabilistic queries. So we can select one or more variables from X that are going to be the query variables. We're going to select other variables from X that are going to be the evidence, and we can pose a probabilistic query in order to check what is the probability of the query given the evidence. On the other hand, when we have a discriminative model, it's going to be fixed for that task. So the discriminative model that approximates the probability of y given x, and being y one attribute that's going to be special, that's going to be the class attribute, is only useful to answer the query, what is the probability of y given x. And in this case, it can be enough to solve a task like classification, in which we want to know what are the probabilities for each class label and select the one that has the highest probability. Just a note here is that the discriminative models that we have in machine learning, they may not directly approximate this probability here. They may approximate this probability in an undirected way, for instance, trying to create a map between the input x and the class label y. But even though that the generative models are interested in modeling P of x, there is nothing that will restrict us to use those models into classification problems. We just pick one attribute to be the class attribute y, and we compute the probability of y given x from the probability, the joint probability of y and x. And we have done this before, and we had one lecture about using some of the generative models that we discussed in this course in classification problems, and also we have one assignment about this topic. But if we use the generative models for classification, what is better? The generative model or the discriminative model? That is a question that has been asked many times in machine learning. And generative models are particularly interesting in the case that we have missing data. And the missing data may occur in the training cases. In this situation, we frequently use variations of the expectation maximization algorithm in order to learn the parameters of the model from data. But it's even more interesting in the case that we have missing data in the test cases. In this situation, we set evidence for the complete data and we leave the attributes with missing data unobserved. And we just run inference, and the inference procedure will eliminate the variables that are not observed, so we can compute the query. And that contrasts with the most of the discriminative models, because most of those models, they require complete data in order to learn or to classify the cases. But aside from this particular situation where we have a missing data, there is a general consensus in the community that the discriminative models are better than the generative models when we want to perform classification. And people frequently say something like discriminative models have a lower generalization error, or discriminative models, they need less data to train. And that makes a little bit of sense, because if you have a model that is directly trying to estimate the probability of your labels given your data, it should performs better, at least for the classification tasks, than other models that are trying to learn the relationships between all attributes that you have in the data. In the same way, we can expect that the model that is specifically trained for the classification task will require less data than a model that is more general and trying to find the mapping between all the variables that we have in the domain. So one interesting result comes from this paper here. And in this paper, they make a theoretical and also an empirical analysis comparing two classifiers, one generative and another one discriminative. And they selected the naive Bayes classifier and the logistic regression classifier, and we call these two classifiers a generative discriminative pair because they have a very similar assumptions. And in their analysis, they conclude two things. The first one is that the generative model has indeed a higher asymptotic error. So what they're saying is that when we look at a plot like this one, that we have the performance of the generative classifier as we increase the training set size, what we see is that when the training set size is large, so we are approaching what we call the asymptotic error, that would be the error of the classifier when we have an infinite number of training examples. So we see that this asymptotic error for the generative classifier is in fact higher than the asymptotic error for the discriminative classifier. And the second result in this paper that is a little bit surprising is the fact that the generative model approaches its asymptotic error much faster than the discriminative model. So that is showing here in this plot that we have for small training sets, the generative model with a lower error than the discriminative model. And it is approaching its asymptotic error much faster than the discriminative model. So we can observe that we're going to have, in a certain way, two regimes of performance. If we cut here, we have this area where we have small training sets. And in this case, the generative model has already approached its asymptotic error and is performing better than the discriminative model. On the other side, we have this regime here with larger training sets, and in this case, the discriminative model, it approaches its lower asymptotic error and performs better than the generative model. So a final topic here is the fact that the generative models, they have that name because they can be used to generate synthetic data. And I'm going to use one example here with a Bayesian network in order to show how we can generate the data according to the probability that is encoded into the Bayesian network. The procedure is very simple. We call it sampling, and we're going to cover this topic again when we discuss the sampling method for approximated inference. And the sampling approach that I'm going to discuss here is very simple. So the idea is that we need to walk through the nodes in the graph in an order so that when we reach one node like this one that has parents, we have already sampled values for the parent nodes. So what we can do is to compute the topological ordering for this graph. So in this case, for this graph, we can have a topological ordering like this. We can start with the node C that has no parents, and we can go to the node S, that is the sprinkler, and from here we can go to the node rain in this way, and at the end we have the wet grass that is going to be the final node. If we have the topological ordering, and we have already seen this algorithm, so in the first tutorial we have covered the topological ordering algorithm that is just an application of the depth search, the depth first search. If we follow the topological order, we're going to give first a value for C, and later on we're going to give a value for S, but now we have already given the value for C, and we're going to follow and go to the rain, and again we have already given a value for C, that's the parent of rain, and when we reach W, we have already given values for S and also for R. Okay, so let me just erase this because we're not going to need this, and let's just sample values according to the topological order for this Bayesian network here. So we started with this node, and I'm going to sample a value for this node cloudy. The procedure for sampling is very simple. We're going to use a random number generator, and we're going to generate a number between 0 and 1 with a uniform distribution. If the number is less than or equal to 0.5, I'm going to sample the value plus C. If it is larger than 0.5, I'm going to give it the value minus C. So we started with cloudy, and use the random number generator, and let's suppose that the output is a number less than 0.5, so we say that's going to be plus C. That is my first value. I continue and go to the next node in the topological order. Let's suppose that the next node is a sprinkler. So now that I know that the first one is plus C, I'm going to focus on this part here of the table, and I'm going to sample again a value now for the variable S, and again I use a random number generator. If the value is less than or equal to 0.1, I'm going to give the value plus S, 0.1. If it is larger than 0.1, I'm going to give the value minus S. So again, let's suppose that the value that I obtain is minus S. So I continue with this process. I go to the next node, that's going to be rain, and I use the information that we sampled the value plus C to the variable C. So now we're going to take and use the random number generator to sample another value here, but now for the variable R. Let's suppose that the number is, I don't know, 0.5, so the outcome here is going to be plus R. And I move to my last node, that is this guy here, and it will depend on S and on R. So we know that we have minus S, so we are in this area here. And we have plus R, so we are in this area here. So now I use the random number generator, and let's suppose that I have a number that is less than 0.9. My final sample is going to be plus W. So this is one complete example that I generated from this Bayesian network. And I continue to do this. So I generated many samples, as many as I want. So I'm going to generate one more. Let's suppose that we start again from the root, and we sample a value for C now. And let's suppose now that the value is minus C. I go to the second node in my topological order, and a sample value for S. Let's suppose now that we got the plus S. And I go to the next node, and I should focus now on minus C. And we sample value again. Let's suppose that the value is like, I don't know, 0.3. So I'm going to be minus R. And I go to the last one, and here we had plus S. So we are in this area here. And we had minus R. So we are in this area here. So I sample again the value. Let's suppose that the number is 0.2. So we're going to be plus W. And I continue doing this. And we can see that by following this procedure, we are respecting the conditional probabilities that are being imposed by the Bayesian network. In fact, the data that we are generating here in this synthetic process do respect the distribution that is encoded in the Bayesian network, to the point that if you want to, we could use that data in order to make inference, and that the results that we get would be an approximation for the probabilistic queries. So let's suppose that we generated, I don't know, a large number of samples, like, I don't know, 10,000 samples. We could use the counts from those samples in order to estimate the results for probabilistic queries. So I could compute something like the probability of plus C by counting the numbers of plus C that I see in the data. And that is exactly the idea that we use in approximate inference by sampling. We generate data according to the generative model, and we use the data points that we generated to answer probabilistic queries. And we're going to see more about this in the lecture about sampling. Okay, so we got to the end of our lecture about the Markov networks, and we haven't seen that the Markov networks are undirected probabilistic graphical models. These models are very common in areas such as image and language processing, because in these domains, it's common to have dependency between variables that have no intrinsic direction. So in many tasks that we have in image processing, we need to compute the map or MPE assignment. And this is so common that we call this approach the map MRF approach. And when we are dealing with this map MRF, we frequently use some specialized approximate inference methods. That happens because the number of variables that we are working with is usually a very high number of variables. For instance, in image processing, it's common to associate one variable per pixel. And also because images are grids, and we can imagine, even though we have never computed that, we can imagine that the tree width of images is very high, because there is a huge difference between a tree and a grid. So we have, oops, there is an error here. So we have a large number of variables, and also we have a high or a large tree width. So that's why we need some special algorithms that will provide some approximate answers instead of exact answers. So We saw also that the variable elimination algorithm, it works for Markov networks. Actually, most of the inference algorithms that I'm going to see, they were designed for Markov networks. So they will involve some transformation of the Bayesian network into a Markov network. One case is the variable elimination algorithm that, as we saw, we compute this interaction graph that is basically the transformation of the Bayesian network into a Markov network using the demoralization step. Finally, we discussed the conditional random fields that are popular discriminative approaches. We compare the discriminative approach with the generative approach, and we saw that the conditional random fields are popular approaches when we have a problem of structure output prediction. Okay, so that's all for this week. Next week is going to be flexibility week, so I'm going to have a small break of 1 week, and we will continue it after the flexibility week, discussing more algorithms for inference. So see you after the flexibility week in week 7.